Welcome back, everyone. In this video lecture, we're going to learn about light energy. And this is from ebook chapter 1, lesson 6. So after watching this video and reading the associated ebook chapters section, you should be able to discuss in relative ease frequency, wavelength, energy of photons, be able to use the equations that are associated with them, be able to identify the various regions of the electromagnetic spectrum, and then do calculations between wavelength, energy, and frequency. So the first thing we want to talk about is light being a wave. And first, before we get into light specifically, let's talk about waves in general. So if you've ever been to a beach that has some barricades on it, you might notice that as the waves come across towards the shore, that we get what are called interference patterns. And this happens when we have waves that are in sync with each other or that are in opposite sync of each other. We call those constructive and destructive interference. So for example, if you have, let's say we've got a wave like this. Let's actually make it a little bit simpler here. So we have one wave like that. If we add it together with another wave and they're in phase with each other, then what we would get is an even larger peak and an even deeper trough. And that's not really to scale or the best drawing, but the idea is that we've added these together and we've made a larger wave. Now, if we have the opposite, so we have two waves that we add them together and they are opposite of each other in terms of their amplitudes and when those coincide, then that would get us a flat line. And so if you take a look here at this image, we can see that there's areas of high amplitude and areas of low amplitude based on the constructive and destructive interference of those waves. Similarly, if we take light and we shoot it through small openings, we see that it also behaves as a wave, meaning we end up with areas of constructive interference, indicated by the bright regions, and areas of destructive interference, indicated by the dark regions. And so diffraction patterns of light is probably one of the best pieces of evidence that we have that light behaves as a wave. And not only is light a wave, but we call it an electromagnetic wave. What that means is that we have magnetic fields and electric fields within light, and they are oscillating up and down, and they're perpendicular to each other. All you really need to know about this is that we call them electromagnetic waves. But this gives them properties, such as the fact that they are a form of energy, and they travel at a constant speed, which is the speed of light, or 3 × 10⁸ meters per second. All types of waves have properties of what we call the wavelength, the amplitude, and then also the frequency. The amplitude you can think of as the height of the wave, and that for light corresponds to its intensity or brightness. The wavelength is the distance between two peaks or the distance between two troughs. This corresponds to when we see light, this actually corresponds to the color that we see when it's visible light. The frequency tells us the number of cycles, the number of times that a given electromagnetic wave goes through its peaks and valleys in a given second. And so if we draw an arbitrary line here, and we say, let's say that these lights, these three different electromagnetic waves are going from left to right. How many times per second do we see, do we pass a given peak? And you'll see that because Here on the top and on the bottom, the wavelengths are essentially the same, that they're going to pass across this red line the same number of times per second because they're traveling at the same speed. However, in the case of wavelength number 2, it's traveling at the same speed, but the distance between the waves from left to right is smaller, so we get more numbers of waves passing through that point at a given, for a given period of time. The number of times that it passes through we call the frequency. That's measured in cycles per second. We also see that that's equal to inverse seconds, or hertz. And so we see that there's an inverse relationship between wavelength and frequency. The analogy I like to draw here is that between if you have a couple that are walking together, and they're walking hand by hand. So we have a couple, and let's say that there's a tall person and a short person. And we want, because they're a couple, they're walking hand in hand, they're going to walk at the same speed. And they have a constant speed with each other. However, if we look at because of their different lengths of their legs, how rapidly they move their legs is going to vary depending upon the length. So the person that has if we look at the relationship between leg length and how frequently, and the frequency in which they have to move their legs, we see that the person that has high leg length, in order to travel at a given speed, is going to have to move their legs less frequently. The person with shorter leg length is going to have to move their legs at a higher frequency in order to maintain the same overall speed as the person that they're walking with. So as we see here, high wavelength is low frequency, in the same way that high leg length is low frequency, and vice versa. So that's our relationship here. They're related through the speed of light, and we see that frequency and wavelength are inversely related. So let's take a look a little bit more about the electromagnetic spectrum. So we have different regions of the electromagnetic spectrum. These are indicated here. We have gamma rays, which have very, very high frequency, X-rays, which are just below that. Then we have ultraviolet or UV light, visible light, which is what we can see, infrared light, microwaves, and then radio waves. And some things you'll notice is that these regions are of differing width, so they cover different total wavelengths. We also can see that the units will sometimes vary in which prefix they use. And that's really just out of sake of convenience. Our brains tend to do well with numbers between 1 and 100, and so we will put UV light in the nanometer range, so that way it ends up between 1 and 100 or so, or 1 and 1,000 nanometers. This here is the symbol for angstrom, and that's equal to 10 to the minus 10 meters. So it's 1/10 of a nanometer. It's important to recognize that the visible region is here between about 400 and 750 nanometers. And what we're going to see, especially in the next section, is that how light interacts with matter is going to depend upon its frequency, about how much energy that it has. Okay? So let's now do a practice problem here, just to see if you can identify the type of light that we have. So pause the video and try this to see if you can get this on your own, and come back and I will walk you through a solution. Welcome back, everyone. Let's talk about the solution to this. So the wave shown below represents a type of electromagnetic radiation, and we want to know what color is it. Okay, so to determine the color, you first need to recognize that the distance that you're given here is not just one wavelength. Remember, a wavelength is a distance between two different peaks or two different troughs. And so it's a little bit tricky to see here how many wavelengths we have. But if we start here and we say, how many times does it go through this entire cycle? Well, it gets back to that same inflection point here and here. So this is a total of 3 wavelengths. If this is equal to 3 wavelengths, then in order to calculate the actual wavelength, we would take that value in meters and divide by 3. And that gets us 5.32 times 10 to the minus 7 meters. Converting that to a more usable number, we would convert that to nanometers. And we see that we have 532 nanometers. 532 nanometers, by looking at the color wheel here, see that it falls in between this range here, and so it's going to be green light. So that's it for this video. Thanks for watching, and I look forward to talking to you later.